Hello everyone and welcome to this webinar. I'm Commander Van Riet from the Chair of Energetic Materials of the Department of Chemistry of the Royal Military Academy. And today I'm going to present our activities related to the aging of ammunition in general and in an operational context in particular. These research and technical activities are being carried out within the research unit on energetic material engineering, mostly in collaboration with ammunition managers from the Directorate General of Material Resources. This presentation is divided into three parts. First, an introduction to the concept of ammunition aging, the need to simplify the problem, the limitation of the scope of this presentation, and some scenarios where risk assessment in relation to ammunition aging is discussed. A study carried out in collaboration with the Land Ammunition Manager is then presented, together with the lessons learned. Finally, an ongoing research project intended to improve the management of aging-related issues in operations is described. Aging is a change of the properties of an ammunition over time, and this concept is not limited to energetic materials. Depending on the complexity of the ammunition, aging of electronic and optoelectronic subsystem, engine components, or non-energetic materials such as seals should be considered. However, the energetic materials, so the high explosives, gun and rocket propellants, and pyrotechnic formulations, are inherently unstable because they must react to release energy. In most cases, they are therefore much less stable than other components, and the lifetime determines the lifetime of the ammunition. For this reason, this presentation will focus only on the aging of energetic materials. The NATO definition of aging of energetic materials is a change in the property over time caused by chemical, thermal, or mechanical processes, as the item is subjected to a real or simulated life cycle environment. It is not my intention in this webinar to describe in detail NATO's guidance and terminology on ammunition aging and related concepts, but the so-called S3 concept is interesting to illustrate that the aging issue is bigger than long-term storage. In fact, it is about always ensuring that ammunition is safe, so does not present a hazard during storage, and suitable for service, so does not present a hazard to the user and its environment during use, and performs as required. Risks need to be assessed at staff level, in most cases using NATO guidance and based on the most serious risk identified, to determine whether aging processes have resulted in a safety or serviceability issue. To enable this risk assessment to be carried out, the risks must be quantified by identifying the failure modes and their associated consequences, and quantifying their respective probabilities of occurrence. The different failure modes are usually distinguished according to three main degradation mechanisms or causes of aging. The first degradation mode is thermochemical aging, or a change occurring in the chemical composition of materials, resulting in unacceptable degradation of safety or functioning characteristics. There are many thermochemical failure modes, and very often they are caused by the ammunition being exposed to high temperatures, a situation typical of operational storage in hot climates. The second type of degradation is mechanical aging, where two main types of mechanical failure can be identified. The first is fatigue, typically as a result of cyclic mechanic loading in the form of vibration. The second is due to the application of stress in excess of the strength of the material. Both lead to the initiation of propagation of cracks and mechanical failure of the material. These modes of failure are usually the result of logistical and operational transport operations and deployment on combat platforms. The third type of degradation is thermomechanical aging, which relates to mechanical stresses in materials induced by thermal effects that leads to mechanical failure and is typically caused by a change of temperature in systems containing materials with different thermal expansion coefficients. These different degradation mechanisms also illustrate that aging of energetic materials is a multidisciplinary issue, mainly involving chemists specialized in energetic materials, and material scientists specialized in polymers. Usually, only the failure modes with major and severe consequences are considered. They've been identified on the basis of lessons learned from the history of ammunition development and use, usually following accidents. Three examples are given to illustrate different failure modes and their consequences. The first one is the thermochemical aging of nitrocellulose-based propellants that are used in all small arms, medium arms, and large arms ammunitions, and in rockets and missiles, where a minimum launch signature is required. These include shoulder-launched anti-tank rockets and some anti-tank guided missiles, including a version of the Spike LR. Nitrocellulose is the main component of these propellants and undergoes a slow spontaneous decomposition reaction even at room temperature. This reaction is normally very slow, and the heat generated can be dissipated into the environment. However, some of the decomposition products are highly reactive species, and they will react with each other or with other components of the propellant to cause adverse effects. The first is gas evolution in the propellant, which leads to the formation of gas bubbles that initiate cracking and reduce the mechanical strength of the propellant. During the combustion, the high pressure causes the propellant grains or block to break. As the combustion surface is not longer controlled, the pressure may exceed the maximal allowable pressure of the combustion chamber and cause it to burst, or the uncontrolled combustion and thrust curve may result in an erratic flight with possible blue-on-blue or collateral damage. The second adverse effect is a reduction in performance due to the breaking of chemical bonds in the nitrocellulose backbone. And the last adverse effect is related to the fact that some decomposition products have the ability to accelerate or catalyze the decomposition reaction. This leads to more heat being generated into the propellant and at some point to a local temperature increase. As the rate of the decomposition reaction is exponential with temperature, this will further accelerate the decomposition reaction and so on. This phenomenon eventually leads to a runaway reaction known as spontaneous ignition. This risk is real, and there are many recent examples of accidents in ammunition storage facilities due to this failure mode, such as in Jordan in 2020, where several tons of mortar ammunition spontaneously ignited, leading to a mass detonation. The second example of failure modes is the mechanical and thermomechanical aging of composite rocket propellants, which are used in the main rocket motor of most missiles, except some man-launched anti-tank guided missiles, and in the solid rocket booster of cruise missiles. The best example is an air-to-air missiles mounted on an aircraft platform, which is subject to vibration and thermal cycling during flight, shock during landing, and so on. To give you a point of comparison, these propellants have mechanical properties comparable to a pencil eraser, and a single crack or delamination will result in an uncontrolled burning surface with the same consequences as described before, namely the bursting of the combustion chamber at launch or an erratic flight. To complicate matters, thermochemical aging of these propellants can also make them more brittle and therefore more susceptible to mechanical and thermomechanical aging. The last example of failure modes is the mechanical and thermomechanical aging of polymer bonded or melt cast high explosives in the main charge of large caliber ammunition, typically 155 mm. Again, cracks and defects are caused by vibration, shock, and thermal cycling during storage, handling, transport, and use on combat platforms. These defects lead to sensitization of the high explosive. And when the projectile is fired, the acceleration can reach 1000 g, leading to adiabatic compression of these voids and a local increase in temperature. And ultimately, it may lead to an inboard detonation of the ammunition, a phenomenon known as setback. As quantifying the probability of occurrence of a failure mode is very complicated and must be repeated for each failure mode of each ammunition. An attempt should be made to simplify the problem. First, defining a general threshold that applies to all ammunition of the same type for a given failure mode would eliminate the need to build a large experimental database for each ammunition. This is only possible for failure modes based on an identical mechanism, typically thermochemical rather than mechanical or thermomechanical aging, for which the thresholds are ammunition dependent. At present, only a generic threshold is widely used to assess the overall risk posed by thermochemical aging of nitrocellulose-based propellants. In addition to this, an overall risk assessment of an ammunition can be simplified by only considering the most likely failure mode with major or severe consequences, namely the life-limiting failure mode of the ammunition. This is possible for simple ammunition containing nitrocellulose propellant. In this particular case, the risk posed by failure modes related to mechanical and thermomechanical degradation mechanisms is significantly lower than that posed by thermochemical aging of the propellant. The definition of the generic thresholds for a critical failure mode is therefore a research topic of great interest to Belgian defense and NATO, as it makes possible to simplify the risk assessment related to aging, thereby limiting the procurement costs and increasing personal safety. It is and has been the subject of many studies in the research unit on energetic materials engineering of the Department of Chemistry. I also have to mention in this part the emerging NATO S3 approach, which can be considered as a solution to simplify the aging issue. It consists of carrying out an S3 qualification program that basically mimics the expected life cycle of an ammunition. First, the life cycle environmental profile is defined, describing all the in-service events and environmental conditions that an ammunition will experience from its manufacture to the end of its life, including storage, logistic transport, operational transport at cold and hot temperatures. Typically, for a given ammunition, this environmental profile consists of a period of long-term storage, deployment to a theater of operation by logistical transport, and deployment on a combat platform until it is used. Then, the sequential tests described in the environmental profile are performed on equipment simulating exposure to temperature, vibration, shock, and so on. Finally, the safety and suitability for service of the artificially aged ammunition after it has undergone this sequential test is assessed by a variety of means, including static and dynamic firings and subcomponent disassembly and analysis. Although promising, this approach is not yet mature in the ammunition market and can be seen as lacking versatility. As a consequence of the simplification of the aging problem, the aging of small arms, medium arms, and large arms ammunitions, and shoulder-launched anti-tank rockets is driven by the thermochemical aging of the nitrocellulose-based propellant they contain, for which there is a generic risk assessment criterion in the form of a threshold based on a measurable property. It greatly simplifies the risk assessment about aging of these ammunition. However, for complex ammunition, such as typically all missiles and larger rockets, there is no such simplification. A full experimental study of each failure mode or an S3 program approach is required, both of which are labor-intensive and extremely expensive. Typically, complex munitions are part of a larger program, and aging issues are addressed by program manager, for instance, such as the US Department of Defense, because they own all the data generated during development, qualification, and use. In other cases, these issues can be addressed directly by the manufacturer, but this is usually more difficult. In most cases, the data remains the property of the program manager or manufacturer, and aging risk assessment is provided as a service through a black box. In all cases, and this is a lesson learned from the aging problems of the Spike anti-tank guided missile, the establishment of a complete experimental database or the completion of an S3 program at the Belgian defense level is not relevant, as an analysis shows that the costs associated with these experimental studies are completely disproportionate to the size of our stockpile. There are different scenarios for which aging risk assessments needs to be carried out. Life extension during long-term storage is usually based on the fact that the storage conditions are constant. So if we can demonstrate that the munition is safe and serviceable by performing destructive experiments on a small fraction of the stockpile, then it is reasonable to assume that the munition will remain safe and suitable for service for a short period of time relative to its history if stored under the same conditions. For simple ammunition as defined above, long-term storage life extension relies on accelerated aging, representative of 10 years at 25 Celsius degrees, followed by measurement of the property of interest and an analysis of the life criterion. During the planning phase of an operation, it is important from a logistic point of view to estimate the service life of the ammunition used based on its intended use on the combat platform or in operational storage conditions. Then it may also be relevant to investigate the possibility of extending the life of deployed ammunition and to evaluate the possibility of reusing it, typically in training after redeployment. Some case study of simple ammunition aging will now be discussed together with the lessons identified. The complex ammunition will not be discussed further in this presentation. Storage conditions, and in particular temperature, are critical for the thermochemical aging of nitrocellulose propellants, which determines the lifetime of simple ammunition, so small, medium, large arms ammunition and anti-tank rockets. Here you can see an example of storage facilities in Belgium where the temperature is completely controlled, and in a theater of operations where the temperature can reach up to 70 degrees in some regions when the ammunition is exposed to solar radiations. A kinetic model describing the underlying mechanism exists for the thermochemical aging of nitrocellulose-based propellants. As it is often the case with this type of reaction, the rate of reaction is exponentially dependent on temperature. The figure shows the equivalent storage time at 15 degrees, the average temperature in Belgium, for different operational storage temperatures. It can be seen that 1 hour of storage at 60 Celsius degrees in operations corresponds approximately to 100 hours of storage in Belgium, and that 1 hour at close to 70 degrees, condition observed in the past in vehicles in Mali, for example, corresponds to a couple of weeks of storage in Belgium. As temperature is a critical parameter for the thermochemical aging of simple ammunition, storage conditions and climate models are required. For planning purposes, rough climate models are usually considered based on the climate zones described in NATO standards. Due to the exponential dependence of the thermochemical aging mechanism of this ammunition on temperature, its aging is significantly accelerated in hot countries, mainly in North Africa, the Sahel, and the Middle East. This is the result of a study carried out in 2018 to estimate the operational lifetime based on the storage conditions, exposed or not to solar radiations, and the climatic zone. It was found that in the most severe conditions, such as ammunition used in the Sahel or in the Middle East, in unventilated containers or loaded on vehicles, the lifetime can be reduced from 10 years in Belgium to 15 months in operations. A number of lessons have been identified from these studies. Other simulation studies, mostly related to service life extension and reuse of ammunition for training after redeployment, have been carried out at the Royal Military Academy for the Land Ammunition Manager and also support the following points. It was found that the NATO generic kinetic model, on which the lifetime extension and predictions rely, based on accelerated aging, is very conservative, as is the modeling of the storage conditions. This leads to unacceptable early disposal of ammunition in extremely hot theater of operations. In the specific case of the aborted BSS operation, the projected replacement and transportation costs of the simple ammunitions were shown to be prohibitive, not because of their unit cost, which is low, but because of the large quantity of ammunition to be redeployed in this context. This demonstrated the importance of improving the accuracy of lifetime prediction in an operational context. Firstly, it was found that the accuracy of the lifetime predictions could be significantly improved by measuring the storage temperature during use rather than using climate models. This requires the use of data loggers to measure the temperature and a data management system to make a decision based on the measured temperature profiled in a storage location. Finally, it is even possible to further improve the accuracy of the lifetime prediction by using a specific kinetic model dedicated to the propellant used in the ammunition. This requires the parameters of this model to be determined for each ammunition, which is relatively labor-intensive. The relevance of this increased complexity is therefore subject to a case-by-case cost-benefit analysis based on the specificity of each ammunition. Identifying these lessons ultimately led to a triple helix project that I will describe in the last part of this presentation, and which is focused on in-service surveillance of deployed ammunition. These lessons led to the expression of the need for the ability to implement an in-service surveillance strategy on a large scale, specifically for arms, munition, and rockets, so simple ammunition. In-service surveillance, or ISS for short, provides the means by which initial service life estimates can be confirmed or even extended to ensure safe and reliable use throughout the required service life. This must be done at minimum cost by implementing efficient ammunition management based on condition monitoring. Considering that the Royal Military Academy Department of Chemistry and the propellant manufacturer PB Clermont or Orenco Clermont have a well-established expertise in the field of characterization modeling of energetic materials, we have seen in this project an opportunity to address these needs, which has been concretized by a triple helix project that is about to start. It consists of improving the accuracy of residual life estimates by measuring real storage temperatures and establishing specific kinetic models for munitions of interest. Our research strategy is aimed at overcoming the technological and scientific obstacles so that Belgian Defence can fully implement an in-service surveillance strategy for the munitions under considerations, namely small arms, medium arms, large arms ammunitions, and shoulder-launched anti-tank rockets. I will now describe each of the main intermediate objectives of this project. First, we need a tailor-made monitoring system that meets the specific requirements of ammunition monitoring in the field. It must be able to withstand an extreme environment in terms of temperature and mechanical constraints. It must not require any maintenance during its 10 years lifetime. It must not pose a threat to the ammunition due to electronic radiation from the communication subsystems or to military security. It must fit into ammunition boxes or, generally speaking, in logistic containers. It must be compatible with operational constraints, and it must be fully integrated with our logistics management software. We intend to integrate around 1,000 tracking units in ammunition logistic containers to record temperature. These will be able to communicate with a receiving platform based on an Internet of Things approach. The data will then be automatically converted into residual life and made available to the material manager through the Belgian Defence Logistics Management software. He will then be able to make a decision on the status of the ammunition based on its actual condition. The low cost of this technology and the data extraction and management routines allows data logger to be placed in a significant number of containers so that a decision can be made on a solid statistical basis. We also need to build an average model to predict the remaining lifetime of ammunition based on a temperature profile. To do so, we will perform accelerated aging experiments at elevated temperatures and measure the residual stabilizer content by chemical analysis for thermochemical aging characterization and measure the maximal pressure by instrumented firing in weapon for ballistic aging. In some cases, we will also need to perform heat flow calorimetry experiments as part of the physicochemical aging characterization. We will characterize about 30 different types of ammunition. We will also validate and consolidate the model by deploying around 1,000 tracked ammunition logistic containers, ammunition boxes, in a real operational environment. They will be deployed for a few years in regions with extremely hot climates and then redeployed. The duration of the deployment will correspond to realistic operational lifetime of the ammunition, and we will then carry out destructive tests and compare the predicted residual life with that measured to validate and consolidate the model, again based on a very large dataset to be relevant. This concludes my presentation. After an introduction to the aging of ammunition in general and a discussion on how to simplify the problem, the scope of this presentation was limited to simple ammunition, namely small arms, medium arms, and large arms ammunition, and anti-tank rockets, for which the thermochemical aging of nitrocellulose propellants determines the lifetime. Lessons were then identified on the basis of case studies. These lessons form the basis of an ongoing LLX project aimed at improving the accuracy of lifetime prediction in an operational environment in the future. Thank you for your attention, and I'm now ready to take your question.